Hi, good afternoon. Today's little mini lecture is on non-minimum phase root loci. Now, what do we mean by this? Well, it's very much a function of the zeros in the transfer function. So if we've got, say, an s plus 1 as our zero, then the zero is in the left half plane, and that would result in a normal root loci. However, if we've got a 0 in the right half plane, like say s minus 1 equals 0 or 0, 1, then this is a right half plane 0, and this results in a change in the type of root loci plot we get. And we now get what's called a positive feedback root loci. And whether you get a positive feedback root loci or the normal negative feedback root loci just solely depends on the right half plane zeros. And if we've got an odd number of right half plane zeros, then we get a positive feedback root loci. If we get none at all, or an even number, we get a negative feedback root loci. And to demonstrate this, we're going to look at a little example, and here's the example here. So we've got a non-minimum phase 0 here. S is 1, we've got an s plus 4, s plus 8, s plus 10 and s plus 15. Now when we come to plot the root loci, we have to work out a number of parameters. So we've got n, number of poles, m, number of zeros, r, difference between poles and zeros, sigma, which is the sum of the poles minus the sum of the zeros divided by r, and also an angle equation for the infinite loci. So with our classical negative feedback root loci, we have the infinite zeros, the angles are given by 180 over r. Now with positive feedback root loci, the n, m, r and sigma are exactly the same, but this time the angles associated with the infinite root loci are now given by 360 over r. So this is the subtle difference between the two. And if we were to use the angle criteria, the angle criteria here uses minus 180, whereas here we would use 360. So let's start off by having a look at a root loci for this system here. So first thing we notice, negative sign there. That's telling us it's got an odd number of right half plane zeros, so it's going to be these rules now for working out root loci. So we're going to get n, m, r and sigma first of all. They're the first things that we need to compute. So n, number of poles, 1, 2, 3, 4. 4 poles. Number of zeros, 1. R now is n minus m, which in this case would be given by 3. Sigma, remember, is the sum of the poles minus the sum of the zeros divided by r. So sigma will be minus 4 and minus 8 will be minus 12, minus 22, minus 37. So it'll be minus 37 and minus, and then the 0 is at plus 1, so it's minus 1 divided by 3. So sigma will be minus 38 over 3, which is, so sigma will be minus 12.66. So this is the next thing to calculate. Now, the next thing we've got to watch out for is the shape of our infinite loci. And the shape of our infinite loci this time are given by this equation here, which is 360 over r. So we have a slightly different now set of infinite loci patterns, which I'm going to put down here. So let's consider some infinite loci patterns for different values of r. So we can put them along here. So this can be, say, r equals 1, r equals 2, r equals 3, and say r equals 4. So when r is 1, the infinite loci is 360 over 1. So its infinite loci is going in that direction like that. That's 360 over 1. Well, it's 2, it's 360 over 2, which is 180. This time one will go that way and one will go that way. So that's the r equals 2. When r equals 3, it's 360 over 3, which is 120. So this time I'm going to get one down that way, one up there and one down there. With that angle is 120. When r is 4, 360 over 4, 90. So we're going to get one going that way, one going that way, one going that way, and one going that way. So these are the shapes now associated with infinite loci. And where this point is here is actually sigma along. So in our case, sigma is minus 12.26. So if we use some scales on these, I'm going to call that minus 5, minus 10, minus 15, minus 20. That can be 5, 5 and 10. Remember, this is j that way, real that way. So our sigma is minus 12.66 and r is 3. So we're going to have some infinite loci, say about there somewhere. And we can put these on now and we can draw these at an angle of 120 degrees. Like that. And with this. Another one going down this way. So here now are our infinite loci, and this point here, remember, is minus 12.66. Now, next stage, we're doing our root loci, is to plot now the poles and the zeros on the diagram. So I've got a pole at minus 4, it's got a pole about there. I've got a pole at minus 8, so I've got a pole about there. I've got a pole at minus 10, so that's easy, it's going to be there. And another pole at minus 15, so there's my 3 poles. And I've got a 0 at plus 1. So I've got a 0 there at plus 1. Now we come to do the root loci on the real axis. Now this one is also different to this one. So this, in fact, the root loci rule for this one is completely back to front to this one. So this one starts, you also get a root loci along here, always, until it comes to the first pole or 0. Doesn't matter if it's a pole, then it switches off. Then it comes on again, till it meets another pole or 0, then it switches off, then goes off, then it comes on again, and then goes off. So these now are the root loci on the real axis. So it's the same rule as we had here, but it's back to front. So we have a root loci, then we meet a 0 or a pole, that's one thing. One thing now is an odd number of things, so it isn't a root loci. Meets two things, even number of things, so it is a root loci. 3 things, odd number of things, no root loci. 4 things, even number of things, root loci. 5 things, odd number of things, no root loci. So that's our root loci on the real axis. And our next stage now is to know that 3 poles go to infinite zeros, that's red lines, and 1 pole goes to the finite 0. So these 2 poles now will come together, meet up, and approach the asymptote and the asymptote. So they've come in that way and gone around that way. These 2, one of them's got to go there, and one's got to go down that way. So the way they're going to do it is they're going to come together, meet up as a complex conjugate pair, like this. So these are going to come together and go round this way. Then one goes that way, one goes that way. So these are the arrows on our root loci. Like that. So this now is our final root loci plot for our system here. Now the next thing that we might be interested in doing is working out that point there. That's the point at which the system goes from being stable on this side to unstable on that side. Now, in the root loci technique, we can locate a point on the root loci by using the angle criteria. But because this is a positive 0 here, then it means we're using this rule here. So therefore, our angle criteria now will have to take into account the fact the sum of the poles of the zeros minus the sum of the poles of the sum of the phases of the zeros minus the sum of the phases of the poles is equal to minus 360 degrees. So let's just have a look now how we might do that. So we can apply the angle criteria, which says that the sum of the zero angles minus the sum of the pole angles is equal to 360 degrees. It's 360 this time as opposed to 180. And we can do this now by going back to this diagram here and guessing this point here. So it will be advantageous now, I think, to just quickly